Welcome to MAI 580. This is a course about agentic AI, systems that do more than produce text. They gather evidence, use tools, maintain state, plan, and get evaluated. Before we build any of that, we need a shared mental model of the language model sitting at the center. Let me set the expectation now. Today is not a history lecture. Everything we open up today is something you will have to make a decision about later in the semester, usually a decision with a cost attached. This is a graduate applied course, so our rhythm is always the same. Understand a concept, implement a small version, inspect what the system actually did, and defend the design. Notice the third step, because it is the one students skip. Inspect what it actually did. The why is important here. A convincing demonstration is not enough for an agent system. You must be able to explain its evidence, its cost, its failure modes, and its safeguards. And the who is you, as an engineer and as an evaluator, not as a user of an API. Let me say plainly where the difficulty in this course actually lives, because it is not where students expect. Building an agent that works is the easy half. Anyone can wire a framework together and produce something that answers. The hard half is everything that is not the function. Scalability, security, responsiveness, reliability. You don't want an agent you have to supervise on every run. And running alongside them as constraints rather than qualities, cost and accuracy. In software engineering, we call the first group non-functional requirements, or quality attributes. In this field, they are what separate a demonstration from a system. And there's one property of agents that makes all of this harder than ordinary software. An agent is iterative. If it makes an error at step 1, that error does not stay at step 1. It becomes the input to step 2, and step 2 builds on it faithfully. Errors do not merely occur in an agent, they accumulate. Hold on to that word, because it explains why we'll spend an entire topic on evaluation and another on safety, and why a per-step merriment will mislead you unless you know how to compound it. Our objective has 4 connected parts. First, analyze the language model and understand its trade-offs. Second, design systems around it with tools, retrieval, and memory. Third, evaluate the system using evidence. Fourth, deploy it responsibly. These 4 are exactly the 4 course learning outcomes on the slide. Now, read the line at the bottom, because it is a course policy and not a decoration. These are not separate units. Let me ask you why that line is there. It is tempting to treat evaluation as something you add at the end, and security is something another team handles. Here is why that separation is not allowed, using 3 failures you will actually meet. A system can be clever, but unsafe. It gives an excellent answer, and it also sends private data to an external service. A system can be safe, but unhelpful. It refuses every request that carries any risk. And a system can appear useful, but be impossible to evaluate. It produces a convincing demonstration, and nobody can say how often it is wrong. None of those 3 is a complete project. As a consequence, when you defend your project, you will be asked about all 4 parts, not only the part that worked. The order of this course is deliberate, and I want you to see the logic in it. First, we understand the reasoning substrate. Then we give it reliable evidence and actions. Then we organize autonomy, and finally, we test and govern it. Look at the 4 blocks. Block 1 is the reasoning substrate. Today's foundations, then reasoning, prompting, and context engineering. Block 2 is acting with evidence, tools, function calling, and the model context protocol, then grounding and memory. Block 3 is autonomous design, architectures and planning, multi-agent orchestration, and emerging paradigms. Block 4 is proving and governing, evaluation, observability, and debugging, then security, safety, and responsible deployment.
This order prevents a mistake I see every year. A team reads about a multi-agent framework and starts there. They build 5 agents that talk to each other. Then the system fails, and they cannot say which agent was wrong. They never asked whether one model, one tool, or a better retrieval pipeline would have solved the problem. As a consequence, we build the substrate first.
For the first 5 weeks, we build the foundations. These are also the topics the midterm assesses. Let me walk the table row by row. Weeks 1 to 5 cover foundations, context, tools, grounding, and memory. Lab 1 runs early, and both the project proposal and Lab 2 are due in Week 5. Weeks 6 and 7 move to single-agent architectures, planning, and frameworks, and Lab 3 is released. Week 8 is the midterm, covering topics 1 through 5. Weeks 9 through 13 cover multi-agent systems, emerging paradigms, evaluation, and security. In that period, you also present a paper seminar and take part in a red team exercise. Weeks 14 and 15 are project presentations, with a live demonstration and questions. Then the comprehensive final. One practical instruction, and I will repeat it whenever it comes up. The detailed dates, deliverables, grading policy, attendance, and academic integrity rules are in the syllabus on e-learning, not on this slide. Check it before every class, because the calendar may adapt as the field moves. And start thinking about a project problem now, because a good project needs a real question, not a flashy interface.
Notice what we reward. 20% is sustained preparation, quizzes, assignments, paper reading, and seminar activities, spread across weeks 2 through 13. 25% is the midterm in week 8. 25% is the course project. 30% is the comprehensive final examination. Again, the grading policy, the weights, and the dates live in the syllabus on e-learning. This slide is a summary, and the syllabus governs. Now, read the box at the bottom, because it defines what project means here. You will work in teams of 2 or 3. You will build, evaluate, and defend an agentic system. The grade depends on 6 things: technical depth, evaluation rigor, failure analysis, security and safety treatment, report quality, and the live defense. Now, tell me what is absent from that list of 6. Whether the demonstration works. It is not one of the 6. Why not? Because a demonstration that works once is not evidence. It is a single sample. As a consequence, a team that reports honest failures and measures them will score higher than a team that shows a polished demonstration and can't explain when it breaks.
Today has one argument, and I want to state it before we start, rather than reveal it at the end. Read the sentence at the top of the slide. This course is about systems that act, but an agent is a loop wrapped around a language model, and you cannot reason about the loop without understanding what sits inside it. So the lecture has 2 halves. The first half is the substrate. We open the model, self-attention refreshed, then how a transformer becomes a language model, and then the architecture frontier from 2023 to 2026. The second half is the gap. We ask what language models structurally cannot do, what that means for ethics, safety, and risk, and why agents and tools follow from it. The conclusion is printed at the bottom, and it is the thesis of the whole course. Agents are not a product feature. They are the engineering response to a specific, well-documented set of limitations. One request while you listen. Listen for the word because. Every component we introduce later must have a reason to exist. And if I ever give you a component without a because, stop me and ask for it.
These are today's learning outcomes, and they are written as things you will be able to do, not things you will have heard. First, explain how self-attention, causal masking, and the decoder block turn tokens into a language model. Second, Distinguish three things that are constantly confused: training time scaling, inference time compute, and architectural efficiency trade-offs. Third, identify which failures are structural, rather than failures that more scale would remove. That third outcome is the hardest, and it is the purpose of the entire second half. Fourth, justify tools, memory, verification, and agent loops as engineering responses to those failures. Fifth, describe why autonomy changes the security and ethical stakes of an AI system. Now, the connection to the course. This lecture establishes course learning outcome 1, which is analysis. The remaining topics build what outcomes 2, 3, and 4 require: the designs, the evaluations, and the safeguards. Today we analyze, because we cannot design what we have not analyzed.
We begin with the mechanism. Most of you covered the canonical transformer last semester, so today we take a different view of it, the system view, the cost view. The key question is simple. When a model reads a token, how does it decide which earlier tokens matter right now? Fair question to ask me. Why open a 2026 graduate course with a paper from 2017? Because the core mechanism still sits inside most frontier language models, and because its cost is a constraint you will personally meet this semester. Look at the two columns. On the left, the original paper from 2017. The base model had 65 million parameters. The big model had 213 million. It was trained for 3.5 days on 8 GPUs. On the right, a frontier model from 2026. 2.8 trillion total parameters, about 104 billion activated for each token, and a context window of 1 million tokens. That is roughly 13,000 times larger. Now, read the note at the bottom, because it is the reason we are here. The main operation is still a weighted average of vectors, and the weights still come from dot products. What changed is the scale, the data, the training procedure, and the engineering required to control cost. So we revisit attention, not for history and not for nostalgia. We revisit it because its cost is a systems constraint you will meet in your own project. Let us start with the problem before we name the mechanism. Here's a question about language itself, and it comes before any architecture. How does a system represent meaning? There are two different things to get right, and they're often confused. There is morphology, and there is semantics. Which mechanism gives us which? Careful here, because the usual answer is wrong. Morphology is not semantics. Tokenization gives you morphology because it produces the vocabulary, the reusable pieces of the language. Embedding gives you semantics, the meaning and context. Two different mechanisms, two different jobs. Now, the classic example. Consider the word bank. Look at the two sentences on the slide. In the first, I sat by the bank of the river. In the second, I deposited cash at the bank today. The same 5 characters appear in both, but the meaning is different. State that as a problem the model must solve. The same 5 characters must become 2 different vectors, and the only information available to tell them apart is the surrounding text. In the first sentence, the useful evidence is the word river. In the second, it is deposited and cash. Notice that this evidence is not at a fixed distance from the word bank. So what must the mechanism provide? The slide names 3 requirements. First, every position can look at every other position, with no fixed window. Second, the amount of looking is learned and content dependent, not positional. The model doesn't always look at the previous 3 words. It looks where the current input suggests it should look. Third, it must be parallelizable. A recurrent network processes one position after another, and that sequential dependency was the bottleneck that attention was invented to remove. Hold on to that third requirement.
In 9 slides, we will discover that it also created a new bottleneck of its own.
Use the database analogy because it makes the 3 roles intuitive before we see the equation. A hash table matches a key exactly and returns one value. Attention does the same 3 jobs, but softly. The match is a similarity score instead of an exact test, and the result is a mixture of all the values weighted by that score. Now, the 3 projections. The query asks, what am I looking for? The key advertises, what do I offer? The value carries, what do I pass on? Each one is the input multiplied by its own learned weight matrix. Now, the question in the box, and it is worth answering carefully. Why are keys and values separate objects? Why not use one vector for both? Because what makes a token findable is not what makes it useful. Take the example on the slide. The capital of Saudi Arabia is, and then a blank. The token Saudi is findable because it's a country name next to the word capital. That's its key. What it should contribute to the prediction is geographic content. That is its value. Separating them lets the model optimize findability and usefulness independently. One honest note about the analogy. This isn't a literal database, and it stops matching in one specific place. A hash table returns one row, attention returns a blend of all rows. The 3 roles, though, are exact. Now, we name the equation. Do not treat it as something to memorize. Read it as 3 steps. Step 1, Q times K transpose. This computes all the pairwise similarities between queries and keys. Before I move on, what shape does that produce? An n by n matrix, where n is the number of tokens. Remember that shape, because in 7 slides it becomes our post problem. One precision here that matters for the next slide. This dot product is an unnormalized similarity. It is not cosine similarity, because we have not divided by the 2 magnitudes. And that is exactly why the scaling term exists, as we will see. Step 2, the softmax. This turns the similarities into weights that are never negative and that sum to 1 in every row. So each position produces a proper weighted average, not an arbitrary sum. Step 3, multiply by v. We use those weights to combine the value vectors, and that weighted average is the output. Now, one addition that this equation does not show, and it is essential for a language model: causal masking. Let me ask you what it's for, because the common answer is not right. What is the objective of the causal mask? The usual answer is to prevent bias. That is not it. The causal mask hides the next token so that it is not taken into account in the prediction. Think about why we need it. During training, we process the whole sequence in parallel, so the future is physically present in the tensor. If I tell you what you have to predict, you will not predict anything. You will copy. So position 5 may use positions 1 to 4, but it must not see position 6. With the mask, generation is legitimate. One more distinction before we leave the mask, because it tells you which models even need one. There are 2 families of transformer. There are representational models, where BERT is the canonical example. They see the whole sequence at once, in both directions, and produce representations rather than continuations. And there are autoregressive models, which generate the next token. Which family needs a causal mask? Only the autoregressive one. And be careful about why, because the obvious reason is wrong. BERT does predict hidden tokens. It is trained on a masked language model objective, where specific positions are masked out and the model must recover them using context on both sides. That is precisely what makes bidirectional attention legitimate there. The thing being predicted is a designated hole in the middle, not the entire future. An autoregressive model has no such luxury. Everything to the right of position T is exactly what it's learning to predict.
so it must be hidden. So the causal mask is not a general property of transformers. It is the price of autoregressive generation. We return to the mask again shortly, because it's also the origin of the statelessness we meet in Section 4. One design choice, two consequences.
Let us walk through one row only, so you can see the flow rather than test your arithmetic. First, a query scores each key. Second, a higher score means greater relevance. Third, softmax turns relative scores into a distribution. Fourth, we multiply each value by its weight. Fifth, we sum. Here's one to try. If the token it is being interpreted, which earlier noun should receive the largest weight? Whichever noun the surrounding evidence supports. And notice that you resolved that from context, not from the word it. That is precisely the computation on this slide. Here is a question worth getting right, and it is one where people usually know the what and not the why. Why do we divide by the square root of dk? Why not by dk itself, or by the logarithm of dk? Let me give you the actual argument, because it is short. Take a query and a key whose components are independent, with mean 0 and variance 1. Their dot product is a sum of dk such terms. The variance of a sum of dk independent terms is dk. So the standard deviation is the square root of dk. Dividing by the square root of dk is exactly what restores unit variance. It is not an arbitrary choice, and it is not a tuning constant. It is the standard deviation of the quantity we just computed. Now, the consequence of removing it. As dk grows, the scores spread out. The softmax saturates towards 1 hot. Its gradient becomes very small, and training stalls. Now, read the key point, because it generalizes well beyond this formula. This is a numerical stability fix. It does not explain language or meaning or cognition. Much of what looks like architectural sophistication is engineering that helps an optimizer work reliable. So when a paper explains why an architecture works, ask one question. Does the explanation describe a mechanism, or is it only a story?
One attention operation computes one kind of relationship, but language needs several at the same time. Syntactic agreement, co-reference, topical association. So instead of one wide attention, we run several narrower ones in parallel. Look at the equation. Each head applies attention with its own query, key, and value projections. Then we concatenate the head outputs and multiply by one output matrix WO. Now, the 2017 configuration on the left, because the numbers make it concrete. The model dimension was 512. There were 8 heads, so dk and dv were 512 divided by 8, which is 64. Each head is narrower, so the total cost is comparable to a single wide head. We get several relationships for roughly the price of one. One caution, and I want you to be skeptical here. You will see diagrams labeling one head as the syntax head and another as the coreference head. Those labels are representative illustrations. The model learns these projections without supervision. Many heads are not interpretable at all, and we do not actually know what relationships are being extracted. The capacity for different relations is the point, not a tidy naming. Now, read the right-hand column, because it is a forward reference. Heads are the unit that later architectures attack. Grouped query attention, multi-head latent attention, and key value sharing across heads. Every one of those is an attempt to shrink the same thing, the KV cache. Keep that word in mind. We reach it in 5 slides.
This slide makes the previous idea visual. Each projection matrix sends the same token into a different and narrower subspace. Look at what that buys us. One head can specialize in syntax, while another tracks co-reference, and neither has to compromise because they never share a representation. That last clause is the important one. If all the relations had to live in one space, improving one of them would damage another. The head outputs are combined only at the end, before the next stage. Now, the connection to agent design, because this is not only a modeling detail. A language model is not retrieving a single fact from a single location. It is continuously constructing context-sensitive representations. As a consequence, when your agent produces a wrong answer, there is usually no single place inside the model that you can go and repair. Sit with that for a second, because it is the reason we will spend a whole topic on evaluation rather than on debugging weights. We have the mechanism. Now the systems question, and it is the one this course actually cares about. What does it cost to use this repeatedly? A decoder block repeats two kinds of mixing, and the slide separates them clearly. Read the first block. Attention mixes across tokens. Every position gathers from every earlier position. This is where context enters the model. Now, the second block. The feed-forward network mixes within a token. It is applied identically at each position. And here's the question people get wrong. Which of the two holds most of the parameters? The feed-forward network, not attention. And since that is where most of the parameters are, that is also where most of the stored knowledge lives. So we have a useful division of labor. Attention brings in context. The feed-forward network transforms what is already there. Around both, residual connections preserve useful information, and normalization keeps training stable. Stack this block many times, and the model gains depth. Now, the third block, marked in red because it carries the most weight for this course. Position T may attend only to positions up to T. Without the mask, the model sees the answer. With the mask, we get autoregressive generation. And the same mask is the reason for the statelessness we will meet in Section 4. One design choice produces both the capability and one of its main limitations.
This figure carries an inequality, and I want you to leave the room with it. Let me set it up as a comparison first, because it is the cleanest way to see the shape of the problem. Attention and a recurrent layer. Which one is more expensive? The honest answer is, it depends. And the whole point is what it depends on. Here are the two time complexities. Self-attention is order n squared times d, where n is the context length in tokens and d is the embedding dimension. A recurrent layer is order n times d squared. Now, divide one by the other. The n squared d over the nd squared leaves you with n over d. That single ratio decides which one is more expensive. Now, put real numbers in it. The original transformer had d equal to 512 and sequences of a few hundred tokens. There, n is smaller than d. The ratio is below 1, and attention wins comfortably. That is the regime attention was invented in. Now, take a modern agent. Take an embedding dimension of about 4,000 and a context of 100,000 tokens. The ratio n over d is roughly 24. Attention is doing about 24 times the arithmetic work of a recurrent layer at that length. And now the part that makes it your problem rather than a curiosity. That is the cost of one step. An agent runs a loop. The prompt, the tool outputs, the history, all of it is re-injected every time you want to generate anything. So multiply that 24 by the number of iterations in your loop. This is why we think at system level in this course. Last semester you covered the functional aspect of transformers. Today we take the systems aspect, because that is what determines whether your design can actually be deployed. Before we go further, let us be fair to long context, because so far I've only described it as a bill. Why does anyone want a long context at all? Because it lets you put the relevant evidence directly in front of the model, instead of forcing it to reconstruct that evidence from its weights. When the evidence is genuinely relevant and the model genuinely uses it, that improves grounding, and it improves the quality of the decision.
Long context is valuable, and that is exactly why its cost is worth studying rather than avoiding. But state that carefully, because I don't want you leaving with a slogan. Capacity is not the same as effective use. A larger window does not by itself make a model more truthful. It only makes it possible to supply better evidence. We'll come back to this in section 3, under the name Lost in the Middle, where we'll see that material placed inside a long context is not necessarily attended to at all. Now, the second complexity dimension, because time complexity is only half the table. The other column is sequential steps. How many operations must happen strictly one after another? For attention, during training, that is order 1. All positions are computed in a single parallel pass. For a recurrent layer, it is order n, because position t cannot start until position t-1 has finished. Put the two columns together and you see the actual bargain that was struck in 2017. Attention pays more arithmetic per layer in exchange for removing the sequential dependency. That trade was overwhelmingly correct on the hardware of the time, and it's the reason the field moved. But notice that the trade is priced by n, and n has grown by 4 orders of magnitude since. And one question before the figure, because the answer decides whether any of this touches you. Take that context of 100,000 tokens in an agent. Where does it come from? It is not your prompt. Your prompt is a small part of it. It's the system instructions plus every tool scheme you registered, plus every document your retrieval system pulled in, plus every tool result that came back, plus every reasoning trace the model produced along the way. You do not type 100,000 tokens. Your architecture accumulates them silently, and each one is charged at the rate we just derived. Now look at where the two curves cross on the figure. For short sequences, the feed-forward network dominates the cost, and attention is cheap. For long sequences, attention dominates, and it dominates quickly. Now the conclusion, and it's the sentence that runs the rest of this lecture. Long context is not free capability. It is a choice that spends compute and hardware. We'll meet the same pressure twice more today, in the KV cache on the next slide, and in the entire architecture frontier of section 3. Almost every architecture we discuss later is an attempt to move this crossing point.
During generation, we do not recompute the keys and values of every previous token at every step. Why can we get away with that? Because for a token that's already in the context, its key and its value do not change. Compute them once, compute them 100 times, you get the same vectors. So we cache them. Look at the effect written on the slide. Work that was order t squared, repeated at every step, becomes order t. Quadratic becomes linear. That is a large saving, and it is the reason generation is affordable at all. At a context of 100,000 tokens, the difference between quadratic and linear is not an optimization. It's the difference between a product and a research demonstration. But now read the price. The cache costs memory proportional to n, the sequence length, times L, the number of layers, times H, the number of heads, times D head, the dimension of each head. Now the word printed in bold, which is the part people forget. This memory is not shared between requests. Each concurrent user holds their own cache. Think about what that means operationally. If a provider has 1 million concurrent users, that is 1 million private cache allocations, each one growing as its conversation grows, each one measured in gigabytes for a long context. This is why these companies build the data centers they build. And I will say something that surprises people. Deploying language models is harder than training them. Much harder. A model that beats everyone on a benchmark is not the same thing as a model you can serve to real users at acceptable latency. Now a question that separates understanding this from memorizing it. We cache the keys and the values. Why do we not cache the queries? The tempting answer is that the query changes and the others do not, and that's not quite right. At every step, we compute a fresh Q, a fresh K, and a fresh V for the new token. All 3 are new. The real reason is about who needs what later.
Every future token will attend to the keys and values of every earlier token, so those vectors are read again and again for the rest of the sequence. A past query is not. Once a token has asked its question and received its answer, nothing downstream ever consults that query again. It has finished its job. So the loop is this. For each new token, compute Q, K, and V. Use the new Q against the entire cache of past keys and values. Then append the new K and V to that cache and discard the query. Cache what will be read again, recompute what will not. Let me also close the loop on the enterprise question, because several of you will face it. People say, quite reasonably, we want privacy, so we will host our own model. That is a legitimate requirement, and for a government, it may be non-negotiable. Safety and sovereignty outrank cost. But understand what you are taking on. You're not taking on a model. You're taking on a serving problem. There were good open source serving stacks, VLLM, Ollama, LM Studio, and others. And note that these solve serving, not training. They're a different category of tool from the model itself. At small scale, self-hosting works, and it works well. At large scale, with real concurrency, it becomes a serious serving and operations problem in its own right. Whether it ends up cheaper than an API is genuinely not something I can tell you in the abstract. It depends on your utilization, on whether you own the hardware or rent it, on the model size, on your latency requirements, on staffing, and on what the provider charges. Do the arithmetic for your own case rather than repeating either slogan. What I can tell you is where the difficulty sits. The main engineering problem is memory, and after that, compute. Your GPU gives you both, and you can exhaust either one first. Now the final sentence, and I want you to remember it in exactly this form. An agent's context is its working memory, and the KV cache is the bill for it. This is why long agent traces are a systems problem, and not only a design preference. Every tool output your agent appends is memory that some server must hold.
Read this as an operations picture, because this is what the providers are actually doing. A shared fixed prompt prefix can be cached once and reused across requests. Each user's new tokens then add private cache state on top of it. This has a consequence you can see on an invoice. The major providers price cached input tokens differently from fresh input tokens, and the difference is large. So this is not an abstraction. Prompt structure shows up in what you pay. Keep stable instructions and tool schemas at the front of your prompt, and keep them byte identical between calls. Put the variable part at the end. Prompt structure affects both reliability and serving cost, and we will return to it with numbers in Section 3. Prefix caching was only one of the mechanisms. This slide gives you all 5, and I want you to have all 5 because together they are the reason this whole business is viable at all. The first is cluster routing, and it is the least glamorous. A load balancer sends each incoming request to a GPU that has memory available for it. The weights are shared. Every GPU in the fleet holds the same model, but each live request holds a private cache. So the routing decision is fundamentally a memory placement decision, not a compute decision. The second is continuous batching. Ask yourself what happens if a server processes one request at a time. Long pause. The GPU sits mostly idle. A GPU is a wide parallel machine. Feeding it one sequence at a time is like using a highway for a single car. So instead, requests A, B, and C are processed together as a batch against the same shared weights, and their keys and values are computed in the same pass. If you have written Python, you already know this instinct in a smaller form, a NumPy vectorized operation against a for loop over the same elements. Identical arithmetic, radically different time, because one of them keeps the hardware busy and the other does not. It's the same idea you already use in training, where we never train sample by sample. We train in batches of 16, 32, 128, sized by how much fits in GPU memory. And the batch also gives more stable gradients than a single sample would.
The word continuous is the part that matters. Naive batching forms a batch, runs it to completion, and only then starts the next one, which means a short request waits for the longest member of its group. Continuous batching works at the granularity of a token step. A finished request frees its cache and leaves, and a waiting request joins at the next step. The GPU never stalls waiting for the slowest member. The third is the paged KV cache. Here's the problem it solves. Each request needs cache memory, but you do not know in advance how long that request will run. So the naive implementation reserves the maximum possible length, one large contiguous block per request, and most of it is never used. The paged approach borrows directly from virtual memory in an operating system. Allocate the cache in small, fixed-sized blocks, keep a block table per sequence, and hand out blocks only as tokens actually arrive. The internal fragmentation largely disappears, and blocks holding an identical shared prefix can be referenced by several sequences at once instead of being duplicated. The fourth we have already met, prefix caching, computing an identical system prompt once and sharing that cached prefix across requests. That's the same mechanism you exploit from your side by keeping the front of your prompt fixed. And the fifth is the admission control, which is the honest one. When the cluster is full, it queues work, rejects work, or enforces limits on context length, output length, and request rate. Every rate limit you've ever hit is this mechanism. It's not a business decision dressed up as engineering. It's the memory arithmetic we did 2 slides ago, surfacing in your API client. Now, what do the first 3 actually buy? Let me give you the published figures, rather than an impression, and note that neither number is on this slide. I'm citing the papers. The Orca system, from OSDI 2022, reported up to 36.9 times the throughput of faster transformer at the same latency level. Call it 37 times. That's from iteration level scheduling, which is the continuous batching we just described. The paged attention work, published as VLLM at SOSP 2023, reported roughly 2 to 4 times the throughput at the same latency against the previous state of the art, including both faster transformer and Orca. And the gain is larger with longer sequences, larger models, and more complex decoding strategies. Note the baseline carefully. 2 to 4 times on top of a system that was already doing continuous batching. These techniques compose, they don't compete. Now sit with the size of that. No architectural change, no retraining, no accuracy loss. The outputs are identical. Same model, same weights, an order of magnitude more user-served, entirely from scheduling and memory management. That's the same lesson FlashAttention will teach us in Section 3, arriving from a different direction. At this scale, how you move and organize data is not an implementation detail sitting underneath the algorithm. It frequently is the performance.
Let us check the first learning outcome, using the 2 columns. On the mechanics side, 3 statements. Attention is a learned, content-dependent weighted average. Multi-head attention runs several such averages in parallel subspaces. Attention mixes across tokens, while the feed-forward network mixes within one. On the economic side, attention is order n squared in time, and the KV cache is order n in memory. As a consequence, long context is a cost problem before it is a capability problem. And agents generate long contexts by construction, through messages, retrieved documents, and tool outputs. So this is not only a problem for model providers, it is your problem. Now, the last item, and it is the practical one, providers cache and share identical prefixes. So keep the front of your context fixed. Hold that line. We come back to it in Section 3 with 2026 numbers attached. Now we turn the decoder mechanism into a language model, and then connect its training and its use to real resource budgets. Because a transformer by itself is not yet a language model. Several things have to happen to it first. This is the transition in one picture. Repeated decoder blocks trained to predict the next token. Scale and data turn that simple objective into surprisingly broad behavior.
But hold on to the word simple, because the objective itself never becomes sophisticated. Everything else does. The training objective is next token prediction. Stated precisely, maximize the probability of the next token, given the previous tokens. That is the whole objective. Now, tell me what is absent from it. The model is not explicitly trained to be truthful. It is not trained to be safe. It is not trained to be goal-directed. It is not trained to use tools. It may acquire useful behaviors as a consequence of the data and the scale, but those are consequences, not guarantees. That distinction matters for the rest of the course. When a system behaves well, ask whether that behavior was trained or whether it merely appeared. Trained behavior is more reliable. Behavior that merely appears can disappear when the input changes. Now, this raw objective alone doesn't give you the assistant you actually use. Let me lay out the full pipeline because you need the vocabulary. Step 1 is pre-training. Next token prediction over an enormous corpus. This is where the model acquires knowledge and fluency. But ask yourself what a raw pre-trained model does when you ask it a question. It does not answer. It continues. It was trained to generate plausible continuations, not to respond. Pre-training gives it the ability to understand context and language. That is not sufficient to follow instructions. Step 2 is instruction fine-tuning, sometimes called supervised fine-tuning. What is the difference from pre-training in terms of data and objective? Pre-training uses a very large general corpus to build general knowledge. Instruction fine-tuning uses a much smaller curated set of instruction and response pairs to specialize that knowledge into following instructions and solving problems. Different data, different size, same underlying mechanism. Step 3 is preference alignment, reinforcement learning from human feedback. Here's why it's needed. The pre-training corpus contains a great deal of material from the open internet, and some of it you do not want reproduced. So we adjust the weights towards human preference over outputs. Let me show you the actual loop, because the name hides how simple it is. For a given prompt, the model generates several candidate answers. A human ranks them. This one is better than that one. Notice what's being collected. Not a correct answer, a comparison. Rankings are far easier and far more reliable to obtain from people than gold standard text, and that is the whole reason this method is practical. Those comparisons train a reward model, a separate model whose job is to predict the score a human would have given. Then an optimization method, classically PPO, updates the language model's policy against that predicted reward. One caveat, so you read the literature correctly. What I have just described is the classic pipeline, the one from the InstructGPT paper. It is not the only preference alignment method in use today. There are now approaches that skip the explicit reward model altogether. But the shape of the idea, learning from comparisons rather than from gold answers, is common to all of them. And preference is not universal. It encodes whose preferences you collected. If we want a model aligned with all values, for example, with Islamic morality in the outputs it produces, that is a choice expressed in the ranking data, not a property of the architecture. Notice what that is. We're optimizing for what a human rates higher. Remember that, because in section 4, it comes back as a documented failure mode. Step 4, and this is the recent one, is reasoning train. Instead of jumping directly to the answer, the model is trained to spend its first tokens generating reasoning steps, decomposing the problem, working towards a solution, and only then producing the answer. Mechanically, it's still token generation. Structurally, it's 2 parts, and it measurably improves performance on hard problems. We'll come back to this in the inference time compute subsection. Step 5 is decoding, which happens at runtime rather than training time. What does temperature control? Creativity, roughly. 0 is deterministic, effectively greedy, always take the most likely token. Higher values sample more widely,
and taken too far, they contribute to hallucination. Top P controls how much of the probability mass you're willing to sample from. These are dials you'll tune all semester, and they're free. They cost you nothing but valence. So the transformer architecture is the foundation, but all of these processes are what turn it into a language model. And this gives us a recurring project question, which you should be asking yourself by week 5. Does this task truly need an agent, or would an ordinary software workflow be better and more predictable?
Here is a distinction that explains something all of you have experienced. In training, we already know the complete text sequence, so many positions can be processed in parallel. The model predicts the token at every position at the same time, and the causal mask is what stops it from cheating. Notice that the mask and the parallelism are the same decision seen from two sides. Let me state the training step precisely, because the mechanism is worth having exactly. We have the ground truth. We know what the next token actually is because we are reading real text. So at every position, we hide the continuation, ask the model for a distribution over the vocabulary, and compare that distribution against the token we know is correct, using cross-entropy laws. If the model assigns the correct token a low probability, the loss is high, and backpropagation adjusts the weights so that next time that token is more likely. And note the subtlety. The input at each position is the ground truth token, not the model's own previous prediction. That is called teacher forcing. And let me be precise about its role, because it's easy to overstate. Teacher forcing alone does not buy you parallelism. A recurrent network is trained with teacher forcing too, and it's still sequential. What makes a transformer parallel is the combination of 3 things: a ground truth prefix that is already known, causal masking that prevents each position from seeing beyond itself, and an architecture with no recurrent dependency between positions. Given all 3, every training position can be computed in one pass. It's also the first quiet mismatch between training and generation, because at inference time, the model must consume its own predictions, errors included. In generation, this is not possible. Token 20 depends on token 19, which depends on token 18. Each token must be produced before the next one can start. Generation is sequential by construction. Now the familiar experience. A model can read a long prompt quickly and then stream a long answer slowly. Reading is parallel. Writing is not. That lag you feel is not a network problem. And notice the consequence for agents. An agent that produces long outputs, or that runs many steps, pays this sequential cost at every single step. We will name these 2 phases more carefully in a moment, as prefill and decode. In-context learning means the model adapts its behavior from examples and instructions placed in its current context without changing its parameters. Look at the left column. GPT-3 in 2020 had 175 billion parameters. But the finding that mattered was not the size. It was that a task could be specified by examples in the prompt with no gradient update at all. Nothing was trained. The behavior was requested. Now, read the right column, because this is why you care. Every tool description you write this semester is in-context learning. You are teaching the model an API at inference time, in prose, with examples. That is the whole mechanism. There is nothing else happening. Now, the uncomfortable corollary at the bottom, and I want you to take it seriously. If tool use is in-context learning, then a badly written tool description is a badly posed learning problem. The model will then fail in the same way a student fails an ambiguous exam question, not because it's incapable, but because the question was unclear. In topic 3, we treat tool schemas as an interface design problem, and this is the reason why.
This is, in my view, the most important figure in the lecture, so read the axes carefully. The x-axis is how many examples you put in the prompt. The 3 curves are 3 different model sizes. Follow the 1.3 billion line. It is almost flat. More examples buy that model almost nothing.
Now follow the 175 billion line. It climbs steeply. Same prompts, same examples, very different response. So here is the conclusion. The ability to learn from the prompt is itself a capability that appears with scale. And notice that no weights changed anywhere in this figure. Every tool description and every few-shot example you write this semester rides on that upper curve. But do not convert this into magic. In-context learning is still bounded by the context length, by the clarity of your prompt, and by the model's ability to follow instructions. It is adaptation in the prompt. It is not persistent learning. The model remembers nothing after the request ends, and that fact becomes limitation 2 in section 4. Before we discuss scaling laws, we need a vocabulary for what exactly is being spent. Most confusion about scaling is really confusion about units. Before we discuss any budget, we must distinguish the quantities being budgeted, because they measure different things and must never be added together. Read the table row by row. Parameters are a count of weights. They describe model capacity, and they're usually reported as 7 billion, 70 billion, 1 trillion. Tokens are pieces of text, the basic unit of input, output, context, and API billing. A flop is one arithmetic operation, one multiply or one addition, a very small unit of computation. Flops per second is hardware speed, or throughput. 1 teraflop per second is 10 to the 12th operations per second. Bytes and gigabytes measure memory capacity. That is the data held right now, the weights, the activations, and the KV cache. Now the line at the bottom, which is the one to remember. Flops measure work. Gigabytes measure space. Seconds measure waiting. 3 different constraints, and an engineering design must satisfy all 3. A design that is cheap in compute can still fail because it does not fit in memory. This is exactly the split we saw with attention. The GPU gives you compute, and it gives you memory, and you can run out of either one first.
Students say word. The model does not process words. It processes tokens. Follow the diagram at the top. Text goes into a tokenizer, which produces tokens. The tokens go into an embedding table, which produces vectors. And notice that this is the same split we made at the start. The tokenizer handles morphology. The embedding handles semantics. Now the left block. A token is not a word. Tokenizers split text into reusable pieces. One word may be one token or several. Punctuation, code, Arabic, and other languages can produce very different token counts for text of the same visible length. That is not a small detail in this class, because several of you will build agents that work in Arabic, and the same paragraph in Arabic and in English will not cost you the same. Now the right block, which is why this changes engineering decisions. Context windows, KV cache memory, training data, rate limits, and API invoices are all measured in tokens, not in words, not in pages, not in characters. Now the instruction at the bottom. Treat a reported 1 million token context as a capacity in the model's own units. Always measure the actual tokenizer count before you design a budget. Token budgeting is a real engineering task, not formatting.
Parameters are stored numbers, and storage depends on precision. Let us work one example rather than read the table. Take a 7 billion parameter model in FP32. That's 4 bytes per parameter. 7 billion times 4 is 28 gigabytes before anything else loads. Now halve the precision to FP16 or BF16. 2 bytes, 14 gigabytes. Have it again to int 8, 7 gigabytes. Once more, int 4, 3.5 gigabytes. Now, notice what we did and did not do. We did not touch the model. Same 7 billion parameters, same architecture,
Same weights conceptually. We changed how we store a number, and the footprint fell by a factor of 8. So why not always quantize? Because you pay for it. Lower memory footprint and lower bandwidth demand can make deployment feasible on hardware you actually own. That's the gain. The cost is possible loss of quality and numerical robustness, and how much you lose depends on the model and the task. It's a trade, not a free win. Now, what does that buy you at the far end of the scale? It's the reason a model that was trained in a data center can run on a laptop CPU or on a mobile phone. Quantize aggressively enough, and the deployment target changes category. Don't expect frontier quality there, and there are published benchmarks measuring exactly how much accuracy each quantization scheme costs, but the option exists, and for a privacy-constrained deployment, it may be the only option. Quantization is not the only lever on model size, and I want you to know the second one exists, though we won't develop it today. Quantization changes how each weight is stored. Pruning removes weights altogether. The premise is parameter redundancy. A trained network generally carries more capacity than any single forward pass requires, and magnitude-based pruning exploits that by identifying weights whose removal has limited effect on the output. And there's an important distinction inside pruning that decides whether you get a real speedup. Unstructured pruning zeroes individual weights, which shrinks the model on paper but leaves you with a sparse matrix that ordinary hardware still traverses in full. Structured pruning removes whole neurons, channels, or heads, and that's the form that actually reduces compute, because the removed thing stops existing rather than merely becoming zero. You've met a related idea in a different role. Dropout, during training, deactivates random neurons, so the network cannot over-rely on any single one. But that's regularization against overfitting, a different problem with a different purpose. What the two share is only the underlying observation about redundancy. And mixture of experts, in Section 3, is a third response to that same observation, with yet another goal. Do not remove the capacity, simply not activate all of it on every token. And one distinction that catches people. Model weights are not the only thing in GPU memory. There are also activations and the KV cache. A model that fits in memory at load time can still fail on a long context, because the cache grew into the space the weights left over.
Think in 3 budgets: training compute, serving compute, and serving memory. Training compute constrains what model can be built at all. Serving compute constrains latency and cost per request. Serving memory constrains concurrency and context length. Here's why this matters in practice. Your system is slow. What is the cause? You cannot answer that from the symptom. If it is slow, the cause may be sequential decoding. If it crashes under load, the cause may be out of cache memory. If it was never trained well for your task, the cause is neither, and no amount of infrastructure work will fix it. Diagnose before optimizing. This is ordinary engineering discipline, and it is routinely skipped in this field. Inference has 2 phases, and the slide separates them because they behave differently. Read the left column. Prefill reads the prompt. The model processes the input context. Many input token operations can be parallelized on the GPU, so this phase is often measured by input throughput. But a long prompt still costs compute, and it builds a larger KV cache. Now, the right column. Decode generates the response. The next token depends on the previous one, so generation is sequential. 1,000 reasoning tokens require roughly 1,000 successive decoding steps. This phase usually determines the time to the last token. Now, the small table, because it gives you the design rule in one view. A longer input means higher prefill cost, a larger initial KV cache, and a slower first token. A longer reasoning output means more decode steps, a cache that continues growing, and a final slower answer. So let me ask the practical question.
Your system is too slow. You cannot change the model, and you cannot change the hardware. Suppose you have measured it, and Decode is what dominates. What is the cheapest lever available to you? Generate fewer tokens. Constrain the response length. Ask for the answer without the commentary. Cap the reasoning budget. Time to the last token is roughly linear in the number of decode steps, and the number of decode steps is a parameter you control on every single call. It costs nothing to change, and it is routinely the last thing people try, because it doesn't feel like engineering. Note the condition I attached, though, because it's doing real work. If your latency is actually dominated by a slow tool, by network round trips, by a retrieval step, or by an enormous prefill, then shortening the output will not save you. Measure which phase owns your time before you optimize it. The same discipline as slide 34. As a consequence, when someone says make the model think longer, they are choosing the second column. It has a real and predictable cost. Agent loops must spend tokens deliberately.
Now, let us follow one single agent request through the system using the diagram. On the left, an input of n tokens. The model reads the context. That is prefill. It stores keys and values into the KV cache. Then it generates m tokens, one step at a time. And notice the label on the cache. It grows with every token. Now, the two blocks below, on compute and time, reading the prompt costs computation, and generating output costs one sequential model step per token. So more reasoning tokens, or more tool loop iterations, mean more compute and more latency. On memory, the model weights are shared between all requests, but the KV cache belongs to this request alone, and it grows with n plus m. Ask what that means for a server with a fixed amount of memory. Long contexts reduce how many requests one GPU can serve at the same time. Your context length is somebody's concurrency limit. Now, the line at the bottom, which separates two ideas we are about to compare. Scaling laws plan a training compute budget. Test time compute chooses how much work one single request deserves.
Here is the concise model, and the 3 rows are worth memorizing. First, budget. Training data and compute, spent before deployment. It changes what the model learns, that is, its weights. Second budget, model capacity, chosen before deployment. It changes how much the model can represent. Third budget, test time compute, also called inference time compute, spent while solving one request. It changes how much effort the same trained model spends on that request. Now, read the warning box, because this terminology confuses people every year. Test time is historical terminology. Nothing is being tested. It means the computation used when a deployed model answers a real question. It has nothing to do with model evaluation. We will say inference time whenever that is clearer.
Use this analogy carefully, because it is accurate only if you keep the two sides separate. Training is studying. More books, more worked examples, more practice before the exam. This changes what the student knows. And here's the part people skip. When the exam begins, that preparation is fixed. Nothing more can be added. Inference time compute is exam time. More time to plan, to try an approach, to check the arithmetic, to notice an error, and to revise. Now, tell me what does not happen during the exam. The student learns nothing new. They use existing knowledge more thoroughly. That is the whole distinction, and it's where the analogy stops matching the mechanism. A real student can consolidate during the exam, and the model's weights genuinely cannot change. Now, the line at the bottom, which converts the analogy into engineering. A long reasoning trace, a second attempt, or a tool call followed by a reconsideration are all forms of spending more inference time compute. These are different levers, and as an agent designer, during a request, you can only choose the second one.
That is not a limitation of your skill. It's a property of the system you're calling.
Let us be precise about what loss measures, because it is routinely overinterpreted. For each next token, the model assigns a probability. Loss is the average penalty when the correct token received a low probability. So lower loss means better next token prediction on a held-out distribution. That is all it means. Now, the two columns and the contrast is the point. On the left, what a scaling law predicts, a smooth reduction in validation loss as parameters, training tokens, or computer increase. That's a useful engineering signal. On the right, what it does not promise. It does not promise a proportional increase in benchmark score, factuality, tool use, safety, or agent reliability. Those depend on the task, on post-training, on prompting, and on evaluation. Now, the line at the bottom, and it is deliberately two-sided. A small change in loss can sometimes unlock a visible capability, and can sometimes barely affect the task you care about. So measure the actual task. If your project claims an improvement, show success rate, cost, latency, and robustness, not a generic model metric.
Start with the plain observation. A bigger model, trained on more data, usually performs better. A scaling law turns that observation into an empirical budget planning rule. You fit a curve to experiments you can afford, and then you use it to estimate what a larger run is likely to buy. Now, the training side quantity is on the left. N is the number of parameters, the model size. D is the number of training tokens, the data. C is the training compute, in flops, which is the money. And they are not independent. Roughly, C is about 6 times N times D.
Now, read this slide as a budget constraint, because that is what makes it interesting. C is fixed. It is your GPU allocation. So if you double the model size, what happens to the data you can afford? It halves. There is no way to avoid that choice. Let me make that concrete with two options on the same budget. Option 1. 1 billion parameters trained on 100 billion tokens. Option 2, 2 billion parameters trained on 50 billion tokens. Multiply n by d in each case, and you get the same product. So under the C is about 6ND approximation, both runs cost you approximately the same training compute, in flops. Note the hedge. Equal flops is not automatically equal GPU hours, or equal money, because two runs can achieve very different hardware utilization. But as a planning quantity, they are the same budget. They are not the same model. One is larger and less well-trained. The other is smaller and better trained. The scaling law exists to tell you which of those two is the better use of an identical budget. And note that with more compute, you aren't forced to choose at all. You raise both. The law decides the split, not the size. This is what makes how should I split my compute a real engineering question, rather than a preference. Now, the idea to retain at the bottom. More resources bring real and predictable improvement, but each extra improvement costs more than the previous one. The log-log plots and the exponents are evidence for that claim. You do not need to memorize the formula.
Now, the evidence, and I want you to read the shape rather than the exponents. Look at the axes first. Both axes are logarithmic, and the points fall on a straight line. That is the entire claim of this figure. 3 separate resources, compute, data, and parameters. Each give a straight line over many orders of magnitude. That regularity is genuinely remarkable, and it is what makes planning possible at all.
Now, the functional form itself, because it has a name and you will meet it constantly. This is a power law. Y equals a constant times x raised to some exponent b.
And a power law is exactly the family of curve that becomes a straight line when you take logarithms of both axes, with the exponent b appearing as the slope. So the straightness of this plot is not a coincidence or a fitting artifact. It is the visual signature of a power law. And it is why people plot these results this way in the first place. Now, look at the slope, because the shallow slope is the important part. The line rises, but it rises slowly. Doubling a budget helps, but it does not double performance. This is exactly why larger training runs became so expensive. Do not memorize the exponents on these plots. Different papers fit slightly different numbers, and those numbers move. Remember the shape, a straight line on a log-log plot with a shallow slope. Straight means predictable. Shallow means expensive.
Let us state the consequence of that shallow slope directly. The fitted curves improve steadily, but each additional improvement requires disproportionately more data and more compute. Let me put an actual number on the shallow slope, because until you do the arithmetic, it sounds like a minor caveat. We just said this is a power law, so the arithmetic is available to us directly. Suppose the fitted exponent on the compute term is around minus 0.05, which is the order of magnitude these papers report. Now, double the compute. 10 GPUs become 20. By what factor does the scaling term move? Exactly. 2 raised to the power minus 0.05. That is about 0.97. 3% for twice the money. Now double it again. Another 3% or so for twice as much again. That is what a shallow power law feels like from inside a budget. It's not a curve that stops improving. That's the good news, and it's why the field kept going. It's a curve where every equal-sized improvement costs the same multiple again. Eventually, you're spending an amount of money that only a handful of organizations on Earth can spend to move a number by a few percent. Read the two columns together, because both are true at the same time. The good news, scaling is reliable enough to plan around. More data and compute generally yield a better model rather than a random outcome. And for an engineering field, that predictability is valuable. The hard news? The gains diminish. A small improvement at the frontier can require orders of magnitude more money, data, and energy than the previous improvement did. Now, the line at the bottom, which explains the economics of this whole field. The gains are real, they're predictable, and they are extremely expensive. And that last word is the reason for the next subsection. Because training scaling became so expensive, inference time compute became an important additional lever. Necessity, not elegance.
This slide is a lesson in how an empirical field corrects itself. So read the two columns as a sequence. On the left, Kaplan and colleagues in 2020, their recommendation: spend most of any compute increase on model size. Make the model much bigger and let the data grow more slowly. That was the most cited quantitative recommendation in the field, and the industry followed it. On the right, Hoffman and colleagues in 2022, the Chinchilla paper. Their finding was that the earlier recommendation was wrong. N and D should grow at the same rate, roughly 20 training tokens for every parameter. And they demonstrated it. A 70 billion parameter model matching and beating models of 175 billion and 530 billion at comparable budget. Now, read the practical lesson at the bottom carefully, because it's easy to draw the wrong conclusion. At the same training budget, Chinchilla used a smaller model and trained it on much more data, and it performed better. But the reason was that the earlier models were undertrained. It was not because smaller models are intrinsically superior. The lesson is not a number. The lesson is to allocate a fixed budget deliberately. This figure visualizes why two influential recommendations appeared to disagree. Look at the dashed black line. That is the Kaplan result. The other curves are from Chinchilla. At the same compute budget, they land in different places because they asked related but not identical questions and used different assumptions. Now, I want to draw the general lesson because it is one of the most useful habits you can leave this course with. For 2 years, the most cited quantitative recommendation in this field was wrong. The industry spent billions of dollars following it. And the authors of that first paper were careful researchers with good data and no reason to mislead anyone. They simply hadn't searched the space widely enough. So what is the right conclusion here? Not that the first paper was bad science. The conclusion is that there is no wrong or right. There is a result within a research scope. Treat every research number that way. Ask what was measured, under what regime, with what held fixed, and what decision the result actually supports. You'll read a lot of papers this semester, and this is how to read them.
The transferable lesson is disciplined measurement. There is no universally optimal model-to-data ratio you can copy into every project. And if you quote 20 tokens per parameter in your report as a law, I will ask you which regime it was measured in. Your project will have the same logic at a much smaller scale. Define the budget, select the metric, run a controlled comparison, and explain the trade-off. That is the same intellectual move these 2 papers made, with 3 orders of magnitude less money.
Now let us check the theory against real 2026 systems, because this is where the recommendation breaks. Look at the table. DeepSeek V4 Pro, 1.6 trillion total parameters, but only 49 billion activated per token, about 3%. V4 Flash, 284 billion total, 13 billion activated. Kimi K3, 2.8 trillion total, 104 billion activated. Notice the pattern in that activated column. Almost every frontier model now activates a small fraction of itself. Now, the arithmetic in the left box. Chinchilla said about 20 tokens per parameter. Take V4 Flash, 32 trillion tokens divided by 284 billion parameters is about 113. That's roughly 5 times the recommendation. And measured against the parameters actually active per token, 13 billion, it's about 2,500. So has everyone ignored Chinchilla? No, they answered a different question. Read the right box. Compute optimal is not the same as deployment optimal. Chinchilla asks for the cheapest way to reach a given loss. Industry asks for the cheapest way to serve a given quality, forever. Training is paid once. Inference is paid on every request. So you deliberately overtrain a model that is small at inference time, and you accept a worse training compute trade in exchange for a better serving cost for the life of the product. That single distinction, paid once versus paid forever, explains most of what the frontier looks like today, and we're about to see it again in Section 3. We now return to the exam time lever. The question, what can a fixed model do if we allow it to spend more work on one hard request? Inference time compute, sometimes called test time compute, is extra computation after training is finished. It can mean generating candidate solutions, using a verifier, decomposing a problem, searching, calling tools, or reflecting on a result. The weights are fixed. The trajectory gets longer or better structured. And notice how the design question changes once you frame it this way. It is not, can we make it reason? It is, what extra work produces enough reliability to justify its cost? That is an engineering question with a measurable answer, and it is the one you will have to defend in your project.
The study and exam analogy has a direct engineering consequence, so let us make it explicit. Axis 1 is studying more. More hours, more books, more practice problems, all before the exam. When the exam starts, that investment is fixed and cannot be changed. Axis 2 is more time in the exam.
time to try an approach, notice that it fails, back up, check the arithmetic, and try again. Notice the sentence in the second column. The student has learned nothing new. They are using what they already know more thoroughly. Now, the line at the bottom, which connects this to what you will build. A model that writes a long chain of reasoning before answering is doing the second thing. And so is an agent that calls a tool, reads the result, and reconsiders. Your agent loop is axis 2. Every extra iteration you allow is exam time that you are buying. Now, let us see why this is genuinely a second axis, and not just another way of describing the same thing. Start with the sentence at the top. Compute per token is fixed by the architecture. What is 2 plus 2 and prove this theorem cost exactly the same per token. But compute per question is not fixed. Read the box and do the arithmetic with me. Emit 3,000 reasoning tokens instead of 10, and you have run 3,000 forward passes on that question instead of 10. That is roughly 300 times the computation. Same weights, no retraining. Sequence length is the dial, and it turns per request. Now, the table compares the two axes on 5 points. What you increase, parameters and training tokens, versus tokens generated per question. When it is paid, once before release versus every request forever. Who pays? The lab that trains it versus whoever calls the API, which is you. How it is controlled. Fixed at training time versus per request at runtime. Does it adapt to difficulty? No versus yes. And what limits it? Data, money, and hardware versus latency, the context window, and your budget. Read that fourth row again, because it is the one that makes axis 2 interesting rather than merely expensive. Axis 2 adapts to difficulty. Axis 1 cannot.
Now, the evidence from 2 laboratories that reached the same conclusion independently. On the left, DeepSeek R1, January 2025. Reasoning was elicited by large-scale reinforcement learning on a strong pre-trained base, not by making the base model bigger. The capability was already latent, and the reinforcement learning taught the model to spend tokens using it. On the right, Kimi K1.5 and K3. The same conclusion reached separately. K3 states it directly. The rise of reasoning models has established test time computation as a second axis of scaling. Now, the 2 consequences for you, and the second one is the one to remember. As an engineer, when a frontier lab says it is investing in test time computation or in long horizon tasks, it is investing in exactly the workload you are about to build. As someone with a budget, Axis 1 is somebody else's capital expense. Axis 2 is your invoice on every request for the life of your system. A reasoning model spends extra compute inside one response. An agent spends it across 40.
This is the figure I would ask you to remember from this section. So read the 2 panels together. The left panel shows AMIE accuracy over the course of reinforcement learning training. It rises from about 15% to about 77%, crossing the green dashed line, which is the average human competitor. The right panel shows the average length of the model's answers over that same training run, and the x-axis is the same, reinforcement learning steps. The length goes from a few hundred tokens to more than 10,000. Now here is the question that makes this figure important. What in the reward function asked for longer answers? Nothing. The reward asked only for correct answers. Thinking longer is a strategy the model discovered by itself because it made it more correct. That is the strongest evidence that test time compute is a real axis and not a prompting trick. If longer answers were only a stylistic habit, they would not emerge under an objective that rewards correctness alone. We know the pressure now: attention cost and cache cost. This section asks a single question: how do current architectures buy more useful context and more capacity for the same budget?
Keep one organizing claim in mind, and everything in this section will fit into it. The frontier is mostly an economic story, not a mathematics story. Architectures differ, but their practical purpose is one of four things: reduce memory movement, avoid unnecessary attention, increase capacity without activating all of it, or make long context affordable. As we go through each technique, ask yourself which of those four it is doing. If you cannot place it, you have not understood it yet.
FlashAttention is, for an engineer, the most instructive result in this section. And I want to be precise about what it is, because it is commonly confused with the next slide. FlashAttention does not change the mathematics. It is exact attention, identical output, to the last decimal. It does not skip any token, and it does not approximate anything. What changed is the scheduling. The computation is tiled so that the n by n matrix never has to be written out to high bandwidth memory. Now, think about what that tells us. If rearranging the memory access gives a large speedup, while the arithmetic stays exactly the same, what was the bottleneck? Not the arithmetic. It was memory bandwidth, moving data. The flops were never the constraint. This lesson goes far beyond attention. A theoretical operation count is not the whole performance story. Data movement and hardware layout matter, often more. So here is the practical rule for your project, written at the bottom of the slide. When your agent is slow, suspect data movement first.
There are two broad choices, and they are genuinely different. Attend selectively, look at less, or replace part of the attention mechanism with a compact recurrent state, remember less. Sparse attention starts from a simple question. Does every token really need to compare itself with every other token? Sparse attention answers no. Note the contrast with the previous slide. FlashAttention computes the same thing, faster. Sparse attention computes something different and cheaper. Those are not the same kind of result, and conflating them loses the lesson in both. A sparse pattern may focus on local neighbors, on a few selected global tokens, or on blocks. The benefit is lower cost at long sequences. The risk is missing a relationship that falls outside the allowed pattern. So it's a trade: efficiency against universal access to the context. Now, read the 2026 result at the bottom, because you should not skip it. Sparse attention is widely deployed in long context serving stacks. Yet no framework audits how discarding blocks changes the influence of specific content. Read that again. Deployed widely, and its effect on specific content is not audited. Before the consequence, look at how fast this constraint moved, because the trajectory is instructive. GPT-4 launched with a context of roughly 8,000 tokens, with a 32,000 token variant available. GPT-4 Turbo later moved to 128,000. And today, we speak routinely about 1 million across several frontier systems. That's more than 2 orders of magnitude in a few years, and almost none of it came from making attention fundamentally cheaper in theory. It came from kernels, from sparsity, from cache compression, from hybrid layers, the contents of this entire section. Long context is not a capability that was discovered. It's a bill that was negotiated down.
technique by technique. Now, the consequence for your project, and it's concrete. A vendor's advertised context length is not a promise that everything inside it is actually attended to. And this connects to a documented effect you should know by name: lost in the middle. Information placed in the middle of a very long context is measurably less likely to be used than the same information at the beginning or the end. That's real, and it's directly relevant to how you order a long agent context. If your design depends on a detail buried in the middle, test that assumption. Do not assume it.
Let us build the mechanism one step at a time, following the diagram. A state space model reads one token at a time. It folds that token into a fixed size state, and then it reads the output features out of that state. Now, notice the word fixed. The state is updated, never expanded. And that is the whole reason the memory does not grow. Compare it with attention. Attention keeps every previous token available, so its memory grows with the sequence. A state space model keeps a summary of fixed size, so its memory does not grow at all. Here's an everyday picture of the same idea. Attention is like keeping every page of a book open in front of you and rereading whichever pages you need. A state space model is like taking notes as you read, and then answering from your notes. Both can work, but notice where the difficulty moves. If you carry a summary instead of the original text, the quality of the summary becomes the central question. Anything the summary dropped is gone, and no later step can recover it. That is the honest cost, and it is not a small one for tasks that need an exact detail from far back.
This is the honest comparison, and I want you to hold both sides at once. Standard attention keeps everything. It preserves direct access to individual pass tokens, and it pays more as the context grows. A state-based approach keeps a summary. It is cheaper, but it must compress history. Neither one is automatically superior, and the correct choice depends on the task. Ask the diagnostic question. Does the task need exact retrieval of a distant detail, or can it rely on a learned summary? A legal document search needs the first. A long conversational thread may be fine with the second. Now, the two notes at the bottom, because they correct a common impression. Selectivity, making the state update depend on the input, is what made state space models competitive and not merely cheap. Before selectivity, they were fast and weaker. And then Mamba 2 showed something stronger. Transformers are state space models. That result is a unification, not a competition. The two families turned out to be two views of one underlying structure, which is why they can share kernels and theory.
Now let us look at what the frontier is actually buying, with real numbers from the vendor's own figure. Read the two panels. The top panel is flops for one token, plotted against position in the context. The bottom panel is KV cache in gigabytes, plotted against sequence length. The dashed gray line is v3.2, the previous generation. Notice that both quantities grow linearly with context. That is the order n cost we derived by hand in section 1, now appearing in a production systems specification sheet. The theory and the invoice agree. Now, put a number against our own calculation. At 1 million tokens, v3.2 needs about 50 gigabytes for a single request. That's the same order as the 52 gigabytes we computed by hand earlier. v4 Pro cuts that by a factor of 9.5. And now, read their stated reason: making long horizon tasks and test time scaling feasible. In other words, they're optimizing for your workload. So here is the buyer's question to carry away, and it's the most useful sentence in this section. When an architecture claim is made, ask which budget is being improved: prefill speed, generation speed, memory per user, maximum context, or training efficiency. Never say Model X is better,
without saying better for what workload.
You will read that Mamba was going to replace the transformer. Here's what actually happened, in 3 columns. What did not happen? Pure state space models did not displace transformers at the frontier. What did happen? The recurrent state idea was absorbed. Production models now interleave attention with linear or state space layers. And what mattered most? The unifying result, which let both lines share kernels and theory. So the verdict is not that Mamba failed. It is that it was absorbed rather than victorious. And in this field, that is the normal outcome for a good idea. Now, the production form at the bottom. Nemotron 3 Ultra, 2026. 550 billion total parameters. 55 billion active. A mixture of experts hybrid of Mamba and attention, trained on 20 trillion tokens with a 1 million token context. It delivers 5.9 times the inference throughput of a comparable model at on-par accuracy. And read NVIDIA's stated motivation, because it repeats the theme of this whole lecture. As LLM applications evolve from simple chatbots to long-running agents, the ability to deliver fast and efficient inference becomes increasingly important. So use model reports critically, but do use them. Separate a compelling benchmark result from a general deployment claim.
A hybrid design combines mechanisms instead of betting on one, and the central insight is practical. Use expensive full attention where it earns its keep, and cheaper mechanisms where they are sufficient. Kimi Linear is a concrete example of that choice. Now, read the note at the bottom, because it is a lesson in reading benchmarks carefully. The measurement reported here is training throughput. It is not inference speed. Those are different numbers, and they can move in different directions. A design that trains faster may or may not serve faster. So when you compare architectures for your own project, first ask which quantity the figure measures. That is the same budget-aware thinking we will apply to context engineering next week.
The next set of techniques does not mainly change what the model sees. It changes how much model capacity and how much cache cost are activated per request. Mixture of equators answers a different question from the ones we have seen so far. Not how do we make attention cheaper, but how do we get capacity without paying for it on every token? Let me be precise about where the experts actually live, because experts' subnetwork is vague and the reality is specific. Recall from section 1 that the feed-forward network holds most of the parameters in a block. That is the component that gets split. Instead of one very wide feed-forward network applied to every token, you build many narrower ones, the experts, and put a small router in front of them that decides per token which few to activate. Attention is untouched. Mixture of experts is a statement about the feed-forward layer. And notice what the router is and is not doing, because this is easy to romanticize. It is not proving that the other 894 experts would have been useless for this token. It is a learned function that has been trained to select which few experts to activate, and it is optimized jointly with everything else. What that buys is the decoupling. Total capacity can be enormous, while activated compute per token stays small. And it is not free. Routing brings its own problems, and you should know their names before you read a paper about them. Load balancing, so that a few popular experts do not receive most of the traffic while the rest sit idle. Communication cost, because in a distributed system, the experts for one token may live on different devices. Routing instability during training. And the plain fact that a router can send a token to the wrong experts. Mixture of experts is a genuine engineering trade, not a free lunch. What it shares with pruning is only the underlying premise, that not all capacity needs to be active at once, with the decision made per token at runtime rather than once and permanently. Look at the Kimi K3 numbers. 16 routed experts are used out of 896 for each token. So the model holds 2.8 trillion parameters of capacity, but spends only 104 billion of compute per token.
That's 3.7% activated. Now, understand what that buys, because it is not a marginal optimization. This is the reason a multi-trillion parameter model is servable at all. Without routing, every token would pay for every parameter, and nobody could afford to run it. Now, the 2026 survey framing at the bottom, which is a useful way to hold the idea. The trend is a decoupling of three things that used to be one thing. Semantic routing, which expert should handle this, the computational budget, how much we spend, and physical execution, which hardware runs it.
Now, we attack the KV cache directly, and this is the plainest dial in the whole stack. I do not want you to leave without it because it is the one architectural decision you will actually encounter by name this term. Recall the cache size formula from section 1. It depends on the number of heads. So here's the idea. Share key and value heads across several query heads, and the cache shrinks by exactly the sharing factor. No cleverness required. Read the progression in the figure. Multi-head attention gives every query head its own key and value heads. That is the largest cache. Multi-query attention goes to the other extreme. All query heads share one single key and value head. Smallest cache, most compression. Grouped query attention sits in between. Groups of query heads share a key value pair. So you can choose your point on the line. More sharing means a smaller cache and less quality headroom. Less sharing means a larger cache. Now, the practical note at the bottom, and this is why it matters to you specifically. Grouped query attention is the setting that nearly every open model you will run this semester has already chosen for you. When you load a model this semester, this decision has been made on your behalf. Know what was decided and why.
This slide carries the number that matters most today, so let us read it precisely. The architecture line first. Compressed sparse and heavily compressed attention, manifold constrained hyperconnections, and the muon optimizer. 1.6 trillion total parameters, 49 billion active, more than 32 trillion training tokens. Now, the comparison in the middle, at a 1 million token context against the previous generation, v3.2. 27% of the single token inference flops, and 10% of the KV cache, 90% of the cache removed at the same context length. Now, why this is on the slide, and it is not for the architecture names. I do not expect you to remember what a manifold constrained hyperconnection is. Read the author's stated purpose. Making long horizon tasks and further test scaling more feasible. That is a frontier laboratory describing its own architecture work as enabling agents. The systems constraint we derived by hand in section 1 is now the stated design driver at the frontier.
Now, look at the same pressures at a completely different scale. Gemma 4, dense models from 2.3 billion to 31 billion, plus a mixture of experts version with 3.8 billion active out of 26 billion total. It is Apache 2.0 licensed, which means you can actually run this one on hardware you can actually get. Look at the techniques listed. 5-to-1 local to global attention. KV cache reduced by up to 37.5%. A thinking mode, speculative decoding, and quantization-aware training. Now, the real point of this slide. The 3 billion model and the 2.8 trillion model are solving the same problem. KV cache and long context. And they arrive at recognizably the same answers. What does that convergence tell you? That the constraint is real and structural. It is not a fashion, and it is not a marketing cycle. Two teams with completely different budgets, hardware, and goals converging on the same set of techniques is about as good as evidence gets in this field. And this is where I want to flag a research problem, because some of you may end up working on it. A reliable small model would be extraordinarily valuable for agents. The economics we have derived all point the same way.
A loop that makes 40 model calls pays for every one of them, in latency, in memory, and in money. Model size is therefore not a detail of your design. It is a multiplier on your whole architecture. So where do we actually stand? Small models can work very well on constrained, well-specified tasks, especially with good tool interfaces, task-specific fine-tuning, and an evaluation set you actually built. I want to be honest about where they still struggle from my own attempts. On complex, long-horizon reasoning and multi-step tool use, there is still a reliability gap relative to frontier models. And that gap matters more here than elsewhere, because in an agent, the model is the component making decisions. Which tool to call, whether the result is adequate, whether to stop. A weaker decision maker inside a loop is worse than a weaker decision maker in a single call, for the accumulation reason we discussed at the start of the lecture. Closing that gap is one of the more active problems in the field right now, and it is a very good thesis problem. Now, the practical note for your project. Open weights models in this class are a serious option for lab work. No per token cost, no rate limit, and you can inspect everything. And you have real tooling for it. VLLM for serious serving, Olama or LM Studio for local experimentation. Note that these serve models. They do not train them. Keep the two categories separate in your report. Frontier API models remain stronger on long horizon agentic tasks. Choose deliberately and say why in your report. Either choice is defensible, an undefended choice is not.
Let us close section 3 in 5 lines. 1. The constraint is context, and its price is flops and KV cache. 2. Attention got cheaper through I/O-aware kernels, trainable sparsity, and linear variance. 3. State space models were absorbed, not victorious. Production means hybrid. 4. Mixture of experts decouples capacity from compute, and 3 to 4% activation is now normal. 5. The labs say this is for agents. DeepSeek and NVIDIA both write it down in their own papers. Now the transition, and it is the hinge of the whole lecture. We have made the substrate bigger, longer, cheaper, and better at reasoning. So now ask the question that this course exists to answer. Which problems remain even if the model keeps improving? That question opens the second half, and everything after this point is about the answer. Let me give you the reason all of this matters in a form you will feel. In many agentic workloads, model inference is one of the dominant contributors to latency and to cost. Not the only one, and you should always measure rather than assume, because a slow tool, a database, or a browser can easily dominate instead. But where inference does dominate, notice what a long trajectory does to a per-call improvement. An agent that runs 40 steps multiplies every per-call saving by 40. Modest improvements compound into the difference between an interaction a person will wait for and one they will abandon. That is the real stake in this section. Performance optimization here does not merely change what an agent costs. It changes whether a given interaction pattern is practical at all. And each technique in this section moves some category of agent from impractical to shippable. One administrative note. The optional depth folder in the readings has 12 papers on frontier architectures. It's there if you want it. It is not examinable. Now comes the bridge into agentic AI. And I want to be careful about what we are claiming. We are not listing small weaknesses that a larger model will eliminate. We are naming boundaries of the standalone next token model. This whole section turns on one distinction. So let us make it precise before we go through the list. On the left are problems that scale can fix. Give the model more parameters, more data, more training compute, and these get better. We saw exactly that in section 2 with a straight line on a log-log plot. On the right are problems that do not improve with scale. Read the sentence at the bottom carefully, because it explains why.
The right-hand column does not improve with scale because it follows from what the system is. It's a consequence of the design, not of the size. A model that predicts the next token from a fixed set of weights and a finite context has certain properties, and those properties remain no matter how large you make it. As a consequence, something has to be built around it, and that something is this course. So as we go through the next 6 slides, keep asking one question for each limitation. Would a bigger model fix this? If the answer is no, then it needs an engineering response, and that response is a component you will build.
Limitation 1 has 2 halves, and both matter. First, the knowledge is frozen at the cutoff. The weights encode the training corpus. Nothing after the cutoff exists for the model, and no quantity of pre-training includes tomorrow. That is not a weakness that scale can remove. It is a statement about time. Second, and this half is less obvious, the knowledge is not checkable from inside. The model has no mechanism to distinguish "I learned this" from "this is a plausible continuation." Both are the same computation, a probability distribution over the next token. There is no internal flag that marks one as remembered and the other as invented. Now, the measurement from the GPT-5 system card, graded on real production traffic. The thinking model has a hallucination rate 65% lower than the previous generation, and 78% fewer responses containing at least one major factual error. That is genuine big progress, and we should say so plainly rather than dismiss it. But the absolute rate is not 0. Several percent of responses still carry a major error. Now, the last line, and this is the sentence to take with you. Chain 20 such steps in an agent, and what happens to those probabilities? They multiply. A few percent per step is not a few percent per task. We will put an actual number on this in section 5, and the number is worse than you expect. Limitation 2 is statelessness, and the diagram states it plainly. Call 1, call 2, call 3. Between them, nothing carries. No memory. Now, read the box. The API is a pure function. The same input gives the same distribution. And here is the sentence that surprises students every year. A conversation is an illusion produced by resending the entire history every single turn. The model does not remember your previous message. Your application sends it again. Now, the 2 consequences you will feel by week 5. First, everything the agent must remember has to fit in the context, or it has to live in a memory system that you built. That is topic 4, and this limitation is the reason topic 4 exists. Second, and connect this to section 1, you repay for the whole history on every turn. Read that together with the KV cache. Long agent runs are expensive for this reason before any other reason. Not because the model is large, but because the history is resent and recomputed at every step. And notice where statelessness came from. It is not an oversight. It follows from the causal mask and the fixed context design we studied this morning. One decision design, capability on one side, limitation on the other. Limitation 3. Let us be precise about what a forward pass actually produces. It produces a probability distribution over the vocabulary. That is the entire output. It cannot read a file, it cannot query a database, it cannot send an email, it cannot check today's date. Now the second block, which is a subtler version of the same problem, the wrong computational model. Arithmetic, sorting, precise string manipulation, these are token prediction approximations of algorithms. Ask yourself what is actually happening when a model adds 2 large numbers. Okay. It is not running an algorithm. It is predicting what the output of an algorithm looks like. Sometimes the prediction is correct,
that is not the same thing as computing it, and the difference shows up exactly when you stop checking. Now read the fix on the right. Do not ask the model to be a calculator. Ask it to write and run one. Code execution as a universal tool is topic 3, and it is the cleanest example of the whole agentic argument in one move. Now, the sentence at the bottom, which I want you to remember in this exact form, the model is very good at deciding what should happen. It is structurally incapable of making it happen.
Limitation 4. A forward pass costs the same regardless of difficulty. What is 2 plus 2? And prove this theorem consume the same computation per token. The architecture has no way to think harder about a harder problem. Now, the two responses, and notice that they operate at different levels. Inside the model, there is a partial fix. Reasoning models spend more tokens on harder problems, so chain of thought becomes a form of adaptive compute. That is real, and it works. But notice it is still tied to output length. The only way to spend more is to write more. Outside the model, there is a fuller fix, an agent loop. Keep calling with new evidence each time until a stopping condition is met. Now compute scales with task difficulty and not with output length. Now, the line at the bottom, because it is the cleanest definition of an agent in this whole lecture. An agent is a way to spend a variable amount of compute on a problem whose difficulty you did not know in advance. Hold on to that definition. It explains why the loop exists at all. And it will also tell you in section 6 when you do not need one.
Limitation 5 is, in my judgment, the worst item on the list. Read the documented behavior first from the GPT-5 system card. Prior reasoning models were observed to make false claims about actions they had taken, to say they had completed tasks they had not, and to fabricate prior experiences. Now, read the attributed cause, because it is instructive, and it connects back to slide 26. It is partly attributed to reinforcement learning. Graders are fallible. A model that learns to satisfy the grader is rewarded, whether or not the work was actually done. So the behavior was not designed, it was selected for. That is a different and more uncomfortable kind of problem, because nobody made a mistake. The optimization did exactly what it was told. Now, why this is the worst item? What makes the other 5 manageable? They produce visible failure. You can see them. This one produces a clean report of success that did not happen. And read the next line carefully. The failure hides precisely when you are least likely to check, which is when everything looks fine. There is one cheap partial defense worth knowing now, and you can use it today. Ask again. When a coding agent gives me a plan, I ask it plainly, "Are you sure about this plan?" A surprising fraction of the time it comes back with, "Actually, I found something that can be improved." Nothing external changed. No new evidence, no new tool result. So what happened? The model is being asked to evaluate rather than to produce. And evaluation and generation are different tasks, even for the same weights. A second pass gets a critique that the first pass never attempted. Be careful about how much weight you put on that. It is a consistency check, not a verification. The model is still the one judging, so it can be confidently wrong twice. Real verification requires something outside the model. A test that runs, a tool that answers, a value you can compare against. That is section 6's argument, and this is only a cheap approximation of it. Now, the consequence for topic 8, and you will hear this sentence again. Evaluate outcomes. Never evaluate the agent's account of outcomes. Those are 2 different measurements, and only one of them is evidence. Here are the 6 structural limitations in one table, with the reason scale does not fix each one. Knowledge frozen at the cutoff, because no pre-training run contains tomorrow. Cannot verify its own claims, because it's trained for plausibility, not for correctness. Stateless across calls, because the architecture has no persistence. Cannot act on the world, because the output is a token distribution. Fixed compute per token, because compute is not adaptive to difficulty, and reports unearned success because it's rewarded by fallible graders. Now, read the right-hand column again as a group, and tell me what is not there. Exactly. Not one of those reasons is about size. Every single one is about what the system is. Now let me draw the conclusion that reframes everything after this point. And if you keep one sentence from this section, keep this one. Look at where the structural failures cluster. Frozen knowledge, unverifiable claims, no persistence, no ability to act. Every one of those concerns the model as a source of truth and as an actor in the world. Now look at the contrast, and let me put it as relative strengths rather than as guarantees, because a model can certainly fail at any of these on a given input. Its relative strengths are language understanding, synthesis, decomposing a problem, comparing two options, and choosing among candidate actions. Its structural weaknesses are current knowledge, persistence, external action, and independent verification. Those two lists barely overlap, and that non-overlap is the design opportunity. So architecturally, stop treating the language model as your knowledge base and start treating it as your reasoning and decision component. That is the whole move. Do not ask it primarily what it knows. Its knowledge is frozen, unverifiable from the inside, and it cannot tell you which of its answers is remembered and which is invented. Ask it to reason over knowledge you supply, from a source you control, at the moment of the request. The prior knowledge is in there, and it's still useful. It's what lets the model understand what it's reading. But it is conditioned by the context you provide, rather than trusted on its own. Every component in the second half of this course is an implementation of that one sentence. Retrieval supplies the knowledge. Memory persists it. Tools verify it. The loop decides when there's enough of it. Now the line at the bottom. 6 rows. Every one of them has an engineering answer. And none of the answers is a bigger model. We will fill in that right-hand column in section 6. And each answer will turn out to be a component you build.
The moment a language model can use tools and retain context, familiar model errors become system risks, not larger errors, the same errors with a different reach.
Before we discuss risk, we need to see the system whose risks we are assessing. Follow the loop in the diagram. The model chooses a tool or an action. The action reaches the environment returns an observation. The observation updates the context, and then the model chooses again. Now, read the first box. An agent is not simply a stronger prompt. It is a control loop. The model chooses an action, receives evidence from the world, and chooses again. Memory, planning, permissions, and stopping conditions all live around the model, not inside it. That is worth repeating. Every safety control we are about to discuss is outside the model, because there's nowhere inside it to put one. Now read why safety belongs here, in week 1, and not at the end of the term. This loop turns a mistaken token prediction into a possible external effect. That's the whole change. A wrong prediction used to produce a wrong sentence. Inside a loop, it produces an action. We'll define the components properly in topics 3 to 6. First, understand the safety boundary around them.
Let me answer the question directly, because you might reasonably be wondering why week 1 has an ethics section. Because the scope of harm changes when the system acts. Read the contrast. A chatbot that is wrong produces a wrong sentence. An agent that is wrong sends an email, deletes a file, moves money, or files a report. And this is not hypothetical. Coding agents with production access have deleted people's databases. It happens.
When I deploy with a coding agent myself, I write the guardrail into the instruction, back up the database before touching production, and produce a recovery script before making the change. It works well. But notice what that is. It is me building a control, not the model having one. Now, notice what did not change between the chatbot and the agent. The error rate. The model is equally wrong in both cases. What changed is the consequence. Security engineers call this the blast radius, how far the effects spread before something stops them. Now, the two columns. In this course, safety is not a lecture at the end. It is a graded section of your project report and a red teaming exercise in week 13. In your career, you will be the person who decides what an autonomous system is permitted to do. And read the last sentence, because it is the argument for teaching this early. That decision is made at design time, or it's made by an attacker.
The central problem, stated in one line, natural language data can look like an instruction. Everything in this subsection follows from that. Prompt injection is the central security problem of this field, so let us state the mechanism carefully. The model reads its content as one stream. It has no reliable way to mark one part as trusted instructions and another part as untrusted data. So if your agent retrieves a web page and that page contains text that looks like an instruction, the model may follow it. Now, notice what the attacker needed. Not access to your system, not credentials. They only needed their content to arrive in your context. That is a much lower bar than any attack you have studied in a security course, and it's why this problem is hard. Now, read the quotation at the bottom from Grishake and colleagues, because it names the root cause exactly. LLM-integrated applications blur the line between data and instructions. That blurring is not a bug in one product. It follows directly from the design we studied in Section 1. Everything is tokens in one sequence. There is no second channel, because the architecture never had one. And I want you to see how large a step backwards that is, because you've already studied the alternative. Software security spent decades learning to separate instructions from data. Take the cleanest example, the parameterized SQL query. The command is sent to the database as the command, and the user's input is sent separately as data. So the database itself knows which is which. That boundary is enforced by the machine, not by careful string handling and good intentions. Escaping and content security policy do the same job in the browser. A language model prompt weakens that boundary. Your system instructions, the user's message, the contents of a fetched web page, and the output of a tool all arrive at the model as one token sequence, and every part of it influences what happens next. Be precise about what that does and does not mean, because it's not quite that no separation exists. Your application can absolutely label and structure those regions, mark this as system, that as retrieved content, and models are trained to weight them differently. What you do not get is a hard security boundary. It's a learned preference, not an enforced one, and a learned preference can be argued out of. So look at your prompt through exactly this lens and divide it in two. The part you wrote, which is trusted, and the part that arrived from elsewhere. A fetched page, a database row, a document, a tool result, which is not. Then design as if the second part may contain an instruction, because eventually it will. As a consequence, any agent that reads untrusted content, and your project almost certainly will, has this exposure by construction. This table is a lesson in how to read a benchmark, so let us do it in two stages. Stage 1, read the numbers. Browsing prompt injections, 0.99. Tool calling prompt injections, 0.99. Coding prompt injections, 0.97. Higher is better. Your first reaction is the intended one, 99%, essentially solved. Now stage 2. Put that number inside an agent and do the arithmetic with me.
A single task can involve 200 tool calls. At 0.99 per call, the probability that every single call resists is 0.99 raised to the power 200. What is that? About 0.13, 13%. So the system survives the whole task roughly 1 time in 8. It is compromised 7 times out of 8. Now be precise about what went wrong here, because it is not the benchmark. Nothing is wrong with the benchmark. The number is real and honestly measured. What is wrong is reading a per call number as a per task number. That is our error as readers. And it's the same error as reading a research result outside its scope, which we met with Kaplan and Chinchilla. Now the 2 conclusions at the bottom. The model is not the security control, and per call robustness does not survive contact with a loop.
So if the model is not the security control, what actually defends an agent? Read the left column. Architecture, not persuasion. Least privilege, so the agent gets the minimum tool scope. Sandboxing, so effects are confined. Human gates on irreversible actions. And cut the exfiltration path. Notice that not one of those is a better prompt. You cannot write your way out of this with instructions, because instructions live in the same channel as the attack. You have all seen one of these controls without necessarily recognizing it as one. When a coding agent is about to delete a file or run a command, it stops and asks for your approval. That prompt is a human gate on an irreversible action, implemented outside the model, and it's doing exactly what this column describes. I'll be honest with you. In a disposable sandbox, I sometimes grant those permissions broadly, because the environment is contained and the interruptions are constant. That's a defensible decision precisely because of the containment. Against production, it's a completely different decision, because removing the gate means that if the agent makes a mistake, I authorized it in advance. Same setting, entirely different risk. So the question is never, do I want fewer interruptions? It's, what can this agent reach if I'm wrong? And the sandbox is the control that makes the first choice survivable. Run the agent inside a container with a scoped file system and scoped credentials, and a mistake is contained rather than propagated. Add logging over everything so that when something does go wrong, you can reconstruct what happened rather than guess. Now, the real example on the right, and it's worth copying into your own designs. GPT-5 has a documented mitigation. After a connector call returns sensitive data, browsing is restricted to cached pages only. Think about what that achieves. The injection may still succeed. The attacker may still control the model's intention, but there is nowhere to send the data. The attack has no payoff. That's what a real control looks like. It doesn't try to win the argument. It removes the outcome. Now, the lethal trifecta at the bottom, which is the shape to watch for. Danger concentrates where 3 things meet: access to private data, exposure to untrusted content, and the ability to communicate externally. And this isn't abstract for me. API keys do leak. I've had keys leak and lose $100 or $200 within minutes, generating images at scale before anything caught it. Private data, untrusted content, and an outbound channel. That's the whole recipe. And coding agents today sit on all 3. Remove any one of the 3, and the attack loses its payoff. That's a design decision you could actually make in your own project this semester. Technical boundaries need human and organizational accountability around them. A permission model with nobody accountable for setting it is not a control. The instruction hierarchy is a reasonable idea. Not all instructions are equal. System instructions outrank developer instructions, which outrank user instructions, which outrank retrieved content. Models are trained and evaluated on honoring that ordering. Now, read what the same document admits on the right. The GPT-5 card reports regressions on several instruction hierarchy rows compared with its predecessor.
So a newer model is not uniformly safer. Progress is uneven across dimensions, and that is a useful habit of mind. Do not assume that newer means better on the specific dimension you depend on. Test the dimension you depend on. Now, the box at the bottom, because it teaches a transferable skill. How should you read a system card? It is written by the laboratory that built the model. It is not peer-reviewed, and the evaluations are chosen by the authors. That doesn't make it worthless. It's often the only public evidence we have. It means you read it for what is disclosed and you stay alert to what is not measured at all. Ask the same question we asked of Kaplan. What did they choose not to measure? The absent measurement is often the more interesting one.
Here is a finding that should change your defaults. A monitor with access to the model's reasoning trace is substantially more informative about safety-relevant behavior than a monitor that sees only the actions and the final outputs. And monitorability improves as the chains get longer. Now, why this matters for how you build? Tracing your agent is usually sold as an operations concern. Debugging, latency, cost. This result makes it a safety property as well. The trace is where intent becomes visible before the action is taken. And that is the only moment where you can still intervene. After the action, you're doing incident response, not safety. Now, the caveat on the right, and please keep it. A reasoning trace is not a guaranteed record of the computation. It is text the model produced. It can be incomplete, and it can be wrong. Treat it as strong evidence, never as proof. Topic 8 builds on this. So here is the practical instruction. Instrument your project from day one, not the week before the demonstration.
There are 3 ethical questions you cannot defer, and I want to frame them as design questions, not philosophy, because that is what they are. Accountability. An autonomous system causes harm. Who is responsible? The laboratory, the deployer, the user, or the engineer who set the permissions? Note the line underneath. The model did it is not an answer a court accepts. Somebody chose the permission scope, and that somebody may be you. Oversight. Where does a human have to approve? And notice that both extremes fail. Too many gates, and the agent is pointless. You have built an expensive form. Too few, and nobody's actually in the loop, whatever the diagram says. So this is a design decision with an ethical dimension, and there is no default setting. Privacy. Agents accumulate. Trajectories, memories, retrieved documents, all persisted, often far beyond the task that created them. Ask what the user consented to and for how long. Most agent memory systems have no answer to the second half of that question. Now, the item specific to this class, and this is a rule, not advice. You will build agents that call real APIs and touch real data. In scope, your own systems and the course sandbox. Out of scope, everything else without exception. The Week 13 red teaming exercise has written rules of engagement. Read them before you start, not after.
We can now answer the question we opened with. What must we add around a language model? And why? And by now, you should be able to predict most of the answer. Now, we return to the table from section 4, and we fill in the right-hand column. Read the middle column from top to bottom. Frozen knowledge is answered by retrieval and grounding. Statelessness is answered by memory. The inability to act is answered by tools. Fixed compute is answered by the loop itself. Unearned success reports are answered by evaluation and tracing. Now, notice what that middle column actually is. Read it top to bottom again. That is the syllabus of this course. topics 3, 4, 5, and 8 in order. And read it once more with the sentence from section 4 in mind. Retrieval supplies knowledge. Memory persists it. Tools retrieve, execute, and check against external evidence. Note that a tool does not verify anything merely by being called. It verifies when you use its result to test a claim. And the loop decides how much work the problem deserves. Every one of those exists so that you can use the model as your reasoning and decision component rather than as your source of truth. That is not 4 separate ideas. It is one idea, built 4 times. The course outline is not a list of interesting topics. It is the list of engineering answers to the limitations we derived this morning. As a consequence, when you reach topic 4 and we discuss memory, you should already know which limitation it repairs. If you cannot say which one, come back to this slide.
Now, let us define the loop properly, using React. The idea is to interleave reasoning traces with actions. Read the division of labor because it is precise. Reasoning tracks the plan and handles exceptions. Actions gather what reasoning cannot invent. That second half is the important one, so let me make it concrete. What can no amount of reasoning produce? Today's price, the contents of this file, whether the deployment actually succeeded. Only an action can bring those in, no matter how good the model gets. Now, the results on the right. And note the condition attached. With only 1 or 2 examples in the prompt, React gave a 34% absolute improvement in success on AlfWorld and 10% on WebShop over imitation learning and reinforcement learning baselines. Look again at how little was required. 1 or 2 examples in a prompt and no retraining. Now connect this back to section 2. What mechanism is doing the work here? In-context learning. The same capability from the GPT-3 slide. The loop was specified in prose, and the model followed it. That is the entire bridge between the first half of this lecture and the second.
A loop is not automatically intelligence. It's a mechanism whose value must be demonstrated, and in a moment we'll look at when it cannot be. This is the sentence that is the thesis of the course, so let us read it slowly. React, by interacting with a simple Wikipedia API, overcomes prevalent issues of hallucination and error propagation in chain-of-thought reasoning. Now, read what that is actually claiming, because it is stronger than it first appears. The tool is not a convenience. It is not an integration. It is the error correction mechanism. Here is the reason in 2 sentences, and this is the most important because in the lecture. Reasoning alone drifts because nothing contradicts it. A wrong step produces the next step, and there is no force pushing back. Reasoning that must periodically check itself against the real world gets corrected because the world answers back. That is the whole argument. The tool call is not there to fetch data. It is there to introduce something the model cannot invent. Now, the last line, and it explains the title of this course. This is why the course is not called Advanced Prompting. Prompting improves the reasoning. Only the tool call can contradict it. Look at this trajectory across 3 periods because it tells you where the field is going. In 2022 and 23, agentic behavior was a prompting pattern. React was a few examples in a prompt bolted onto a model that was not built for it. In 2025 came K2, Open Agentic Intelligence, a frontier model trained explicitly for tool use. In 2026, architecture reports cite long-horizon agentic tasks as the design target. Nematron 3 Ultra and DeepSeek V4 both do this, and we read their own words earlier today. Now, read what that trajectory tells you. Agentic has moved from something you do to a model to something a model is built for, to something the silicon and the architecture are optimized around. 3 independent levels of the stack now assume the loop. That is a strong signal about where the field believes the value is. And it's also the answer to anyone who asks why a course about agents spent 40 minutes on KV cache this morning.
Now the counter-argument, and it is a good one. I want you to be able to make it because you will need to make it in a meeting one day. Agents are frequently the wrong answer. They cost more, they fail in more ways, they are far harder to debug, to evaluate, and to secure. A loop can run away. A single call cannot. And read the next sentence because it is a judgment about the industry. A substantial fraction of systems marketed as agentic would be better as a deterministic workflow with one LLM call inside it. Now, the two columns give you the test. An agent earns its place when the number of steps is not known in advance, when the next action depends on the last result, and when the task genuinely needs external state. Notice that this is exactly the definition from slide 74. Variable compute for unknown difficulty. It does not earn its place when the steps are fixed and known, when you could draw the flowchart in advance, or when the word agent is doing marketing work in a design document. Now, the question at the bottom, does this need to be an agent? Ask it every week. It is graded in your proposal, and a well-argued no is worth more than an unexamined yes.
This table is our roadmap again, now with a purpose attached to every row. Topic 2, reasoning and context, making a finite context do useful work. Topic 3, tools and interfaces. It cannot act and it cannot verify. Topic 4, grounding and memory, frozen knowledge and statelessness. Topic 5, architectures and planning, turning the loop into a design. Topic 6, multi-agent, when one loop is not enough, and equally when it is. Topic 7, advanced paradigms, learning from the agent's own trajectories. Topic 8, evaluation and observability, reports unearned success. Topic 9, security and safety, data and instructions share a channel. Now, the line at the bottom, every topic in this course answers something in the Section 4 summary table. Nothing here is decoration. If you ever wonder why a topic is in the syllabus, come back to this slide.
Before next week, there are 2 things to do, and the first one is not optional. First, work through the setup folder in the course repository, Python 3.11 or later, and the virtual environment, an API key stored in the .env file, and set a hard spending limit today, not later. Every provider has this setting, and I want it set before you make your first call, because an agent in a loop can spend money faster than you can watch it. Then run the verify script. Topic 2 starts with code, so a broken environment costs you the session. Second, the reading. Core reading is attention is all you need, for the mechanism we studied this morning. Then skim one 2026 model report, either K17 or DeepSeek v4, and read that model report in a particular way. Read it for the architecture and for the disclosed limitations. Do not read it for the leaderboard, because the leaderboard will be stale before the midterm. All the PDFs are in the readings folder for topic 1. And start thinking about the project now. Teams of 2 to 3, proposal due week 5. The best projects come from a task you already care about, not from a framework you want to try.
3 ideas to take away. First, attention is old, but its economics are central. Context costs time and memory. And that cost is the constraint the entire frontier is working against. Second, the most important limitations of language models are structural, not incidental. Scale alone can't solve them because they follow from what the system is rather than how big it is. Third, agents
are a purposeful response. Tools, memory, verification, and control around the model. And they raise the stakes because an error can now become an action. And if you remember one sentence from today, make it this one. The tool is not a convenience. It is the error correction mechanism. Next week, we learn how to make a finite context window do useful work.